Hi everyone, this is Miss Leia, and in this video, we're still going to talk about uniformly accelerated motion, but this time, I'll be presenting you sample problems that are all about UAM happening along the horizontal axis. So for the first problem, it says an antelope moving with constant acceleration covers the distance between 2 points 70 meters apart in 7 seconds. Its speed as it passes the second point is 15 meters per second. What is its speed at the first point and what is its acceleration? So in this kind of problem where we have multiple required to find or multiple variables that we have to solve for, we're going to deal with the RTF or required to find one item at a time. Okay. So first, let's illustrate how the problem looks like first. So there's an antelope and it covers a distance which is 70-meter long. So and there is also making a reference to two different points, okay, separated by the given distance. So let's illustrate that here. So let's say, for example, this is the first point mentioned in the problem, and then this is the second point. It says there that the distance between the two is 70 meters or 70.0 meters. Okay, it also says there that within 7 seconds, the antelope was able to cover the mentioned distance. Okay, and then another information that's given is that the antelope passes the second point at 15 meters per second. Okay, so the velocity at the second point, which is B, is 15 meters per second. Okay, so those are the things that we know about the problem, also known as the given. Okay, now the first question is, what is its speed at the first point? Okay, so obviously the first point that the problem is referring to is this one, the beginning of the 70-meter gap. Okay, and because this happens before the velocity given in this particular point, logically, we should consider this velocity as the initial velocity. So I'm going to label this as v sub 0, and this is what we will call as the RTF or required to find, okay? And consequently, this velocity should be, as it is, its final velocity, okay? So no subscript or whatsoever based on our sign conventions. And then it's also logically sound that we consider 70 meters as the displacement in this problem, because if this is your initial velocity and then this is your final, whatever is the displacement between them is the one that we have to use to plug in the same equation where we're going to apply these two. Okay, so that's our displacement. Now going forward, how do we decide on what equation to use? Okay, so going back to the variables, we have a final velocity, initial velocity, displacement, acceleration, and time. So the question is, which among the kinematic equations should we pick? So if you look at the variables in the problem, we know final velocity, we also know displacement and time, and the required to find is initial velocity. Okay, you should notice that the missing variable in this problem is actually acceleration. And since acceleration is the missing variable in the problem, meaning to say acceleration is not given and it's not also the required to find, we have to pick an equation that does not contain this missing variable, acceleration. Okay, and that should be equation number 2. Okay, so for our choice of equation, that should be d equals initial velocity plus final velocity divided by 2 times time. Okay, now, we have to isolate initial velocity in this equation because that's what we are solving for. And by technique, well, there's no hard rule really when it comes to isolating a variable, but by practice, I usually get rid of the denominator first, because once you get rid of the denominator in the region where you want to isolate something, you'll actually be able to do the rest smoothly. So I'm going to get rid of that denominator 2 by multiplying both sides of the equation by 2, so that it will become 2d equals initial velocity plus final velocity multiplied by time. Okay? And since we're isolating v sub 0 or initial velocity, we have to divide both sides by time so that it becomes 2 times displacement over time equals v sub 0 plus v. Okay, so what happened there? We simply divided both sides by time so that we can cancel time on the right side of the equation. Okay, now we can see that the only variable that is left for us to get rid of is final velocity. And you can simply do that by transposing final velocity on the left because there's a positive sign there, or a plus sign that separates it as a term from the initial velocity. So we're going to do transposition. We're going to transpose final velocity. And this becomes 2d over time minus final velocity equals initial velocity. Okay, now the only task left for us to do is to plug in the given in the problem. So that will become 2 times 70 meters over 7 seconds minus final velocity, which is 15 meters per second. And that will give us the required to find, which is initial velocity. Okay, so that will become 2 times 70 is 140 divided by 7, that's 20. Okay, and then minus 15, you're actually supposed to get 5 meters per second as the final answer for this. So the final answer here for the initial velocity should be 5 meters per second, which is a reasonable answer because I think it's like this is the point where the antelope was just probably building up its momentum until it gets to the 15 meters per second speed in the second point. Okay. Now, how about for the second required to find? It says, what is its acceleration? Okay, so if you think about it, if you want to solve for acceleration, the safest way to go is to disregard the initial velocity, which is 5 meters per second, as a given because it's not ideal that we use something that we only solve for because of the error associated with it. However, if you disregard this initial velocity, you'll actually notice that you don't have an equation where the initial velocity is the missing variable, okay? Well, there's actually equation number 5 for that, but it looks more complicated than these other equations. So the safest way to go, I mean, the best way to go or more convenient way to go is to actually use 5 meters per second as the initial velocity, even though we just solved for it, okay? We're going to treat initial velocity as a given this time, and then we'll solve for acceleration, okay? And I want you to notice, okay, for the sake of convenience, I want you to notice that by definition, acceleration is final velocity minus initial velocity divided by time, right? If you can recall the definition of acceleration. So having all those variables known in the problem, we can actually use that basic equation for acceleration. So let's try that out. Okay, so let's try that out. So acceleration equals final velocity minus initial velocity divided by time. So that's our basic acceleration equation. And then this should be 15 meters per second minus 5 meters per second divided by 7 seconds, okay? And that should give you 10 divided by 7. So it's actually 1.43 meters per second squared. So that's quite reasonable, okay? Because cars, for example, they usually accelerate at around 4 meters per second squared. So nothing surprising with the number for an antelope. Okay, yeah, so that's the correct answer for acceleration. Okay, I hope that's clear. Going forward, let's go to the next item. Okay, so for sample problem number 2, it says that it was once recorded that a car left skid marks that were 290 meters in length. Assuming that the car skidded to a stop with a constant acceleration of negative 3.90 meters per second squared, determine the speed of the car before it began to skid. Okay, so let's analyze the problem. Okay, so it says that there's a 290-meter in length when covered by a car when it skids from a certain velocity coming to a stop. Okay, so let's imagine that scenario. Okay, let's say that the skidding part is from point A to point B, for example. Okay, so A to B, that was the time that the car was skidding. Okay, just to be clear. So during that period, so from point A to point B, the displacement that he was able to cover was 290 meters long. Okay, now take note that the car comes to a stop, right? Because that's the ending point of skidding, right? So what will happen is that our final velocity should be set as 0 meters per second because it stops at that particular point, okay? And then going forward, it's given here in the problem that the acceleration of the car is negative 3.90 meters per second squared, okay? So assuming that it's moving in the positive direction, we would be able to say that the acceleration really should be negative because for stopping action or for skidding to happen, the acceleration and velocity should have opposite directions, okay? So that the car will eventually come to a stop and reach zero velocity. So the negative sign given for the acceleration actually makes sense, okay? We should expect the initial velocity to be positive then. Going forward, determine the speed of the car before it began to skid, okay? So, if this entire path from A to B is the time that the car was skidding, therefore, the speed that we want to know would obviously be the initial velocity or V naught, right? So that's the required to find. Okay. So initial velocity is what we know right before it skids. And then final velocity here is zero because it stops. And as the car skids from that unknown velocity going to zero, the displacement he covered was 290 meters. Okay. And the acceleration rate of the car was negative 3.90 meters per second squared. Okay. So it shows that we can all use these different variables in the same equation because they're pertaining to the same time frame in the car's motion. Okay. So how do we solve for the required to find? Okay. Obviously, 290 meters is our displacement. And if you have initial and final velocity, displacement and acceleration, the missing variable is time, okay? And meaning to say, time is not a required to find, and it's also not known in the problem, okay? So, as the missing variable, we should pick an equation that does not contain time, and that should be equation number 4, okay? So, we're gonna have v squared equals v naught squared plus 2AD. Okay? Now, take note that final velocity is zero in the problem, right? So, we can cancel this in the equation, okay? And the equation will be reduced to V naught squared equals negative 2AD. Why? Because we have to transpose 2AD on the left side, okay? And this will become negative 2AD equals V naught squared. Or if you flip that horizontally, it's going to look like this. Okay, so next step, we're solving for V naught or V sub 0, right? It's the RTF. So you have to square both sides of the equation so that we can cancel this exponent 2 right there. Okay, and this will become V naught, okay, equals square root of negative 2 AD. Okay, that's it. So what do we do next? We just have to plug in the known variables in this particular equation. Okay, so square root of negative 2a squared. Let's take note of that. So let's do some substitution task here. Okay, so negative 2 times negative 3.90 meters per second squared multiplied by 290 meters. Okay, and then use your calculator to execute the operation. So you're gonna have um square root of that. Okay, I actually got 47.56 meters per second. Okay, of course, the next question you should ask yourself is this a reasonable answer? Is this logical? Should I question its value? Okay, so always remember that the last step in problem solving is to evaluate your answer, meaning to say, judge if it is a reasonable number. Well, for me, it's a reasonable answer because, well, cars can actually get as fast as 100 plus meters per second, particularly for sports car. So it's not an impossible speed. It's reasonable. And the car was more or less over speeding depending on where the driver actually is. But this is really a fast speed. Okay. So that's also the reason why you can see that the displacement of the car while skidding was quite big, 290 meters for the car to completely come to a stop. Right. So yeah, it's because of this high speed that is associated with its initial motion. Okay, so let's go check that out. Okay, there we go. The final answer is 47 56 meters per second. Okay. By the way, so the UAM equations can actually be useful for those people who investigate vehicular collisions, for example, because when there is a collision between two vehicles, it's also good to like try to investigate if one vehicle was overspeeding before the collision happened. And the skid marks can actually be used to obtain some useful information regarding the initial motion of the car. Like in this case, we were able to deduce from the 290-meter skid marks that the car's initial velocity was this high, 47.56 meters per second. And you can probably pinpoint some people who are responsible for the accident, for example, in case they're violating the speed limit. So that's the beauty behind that. But of course, I'd like to let you know that it's not just UAM that you need in that kind of investigation. You also have to take into account some other physics concept that will take into account the mass of the vehicle as well to make calculations more accurate. Okay,